next one is a packaged integrated circuit. The next one is a photodetector. You can see the packaging looks completely different, where the packaging is an important part of the design. The next few are just layouts. It's just different devices that we had designed. Okay. So where are we now? So now we're going out of memory and we're looking at, in this moment, what are we doing? So currently, what are we doing? We're doing more than Moore, not more of Moore. So we're going a few nodes back and doing clever things with it. That's what we're doing. And if you look at the list that I've written down there, you will see that they are very, very much the same as the previous one. So we're still building on strengths that we had built up over many, many years. One thing that's different is it's now no longer RF, but micro and millimeter waves. That's one of the important things, is because as the frequencies of the technology go up, some of the other related devices we need, things like antennas, they go into the micron scale. It's no longer millimeters or nanometers, it's now micron scale, which is exactly where microelectronics sit. It's kind of beginning, I'm going to redefine microelectronics. All right, and that's one of the bits why I've done it. It's because in the frequencies that we're working at the moment, the scales we're interested in for devices there are micron scale. All right, so there are some examples. So you'll see many of them look the same. Right-hand side, there are two examples of places we use to manufacture. So the one is AMS, it's Austria Microsystems, which is weirdly enough in Austria. So that's in Europe. The other one is IBM, which is in the USA. We use many other places to manufacture. We have access to many, many places where we can manufacture, but none of them are in South Africa. Okay? But as I say, globally, there are huge companies that are in the same situation. So that's not a bad thing necessarily. All right. We can still design. I call this Moore Plus. So here we kind of use the same technologies, but we add something. So the left-hand side one, we've added some silicon on insulator. So it's extra layers that we've added. It's not part of a standard process. And what we've designed there, that is a light-emitting device. 40 nanometer fingers, you can see there. Very, very small. And it works very well. On the right-hand side, bolometer, it's an infrared detector. So that's a MEMS device. So we need some way, we have the standard manufacturing, and then we add things on top of it. Things that are not part of the standard process. But we add things on top of it that we can do interesting things with. All right. And then the last one, and this now gets to that micron-sized microwave communication circuits. Left-hand side, there's a list of applications. The most important one is communications, and you will recognize things like 5G. People talk about 5G all the time. This is the space we're playing in as far as that is concerned. WiGig, 60 gigahertz Wi-Fi standard that is being developed. And what's interesting is you can see some of the devices on the right-hand side. So the pictures there. The sizes of those devices are millimeters in total, and features on top of it are micron-sized. PCB, so the one at the top there is made with copper on FR4 standard PCB. The technologies, as far as that is concerned, is getting closer and closer to tens of micrometers. They're interesting to us. The middle one is screen printed. The bottom one is also a PCB one. The one on the right-hand side is a circuit that we make with bump bonding. So you have a chip, and you have a PCB, for example, and you have indium bumps, and you use the indium bumps to connect the two together. Those bumps look like components if you do it right. We use those components in the circuits that we do. All right, and that's also a packaging process. My passion at the moment is printed electronics. So we're moving away from subtractive processes and get to additive processes. We only print the devices, we only print the features there where we want them. There's also a lot of work being done to make the materials that we print with much more green, environmentally friendly than the materials that are used in traditional integrated circuit processes. Okay, so point of need, you remember the Yixkay River, you remember the clinics, you remember the bigger hospital. Those places are point of need. If it's diagnostics, it's called point of care, but it's kind of the same thing. So having sensors there where they are needed. I'm also going to move a little bit later into, we're going to try to manufacture them there, or at least closer to where they are needed. But I'll get to that a little bit later. So some of the things that are interesting there is portability, flexible, so we're printing on plastics, printing on paper. Paper is cheap. You can do all kinds of things with paper as a substrate. The size is important, yet we want all the other things that we've had before. We want a fast response. We want low power dissipation. We want to be able to use batteries, getting to printed batteries eventually. It must be stable, it must be durable, you must be able to transport these things, all the other things. It must be smart. It must still be smart, it must be simple, it must be low cost, it must be green. All of those things. Okay, so on the right-hand side, there are some examples of things that we've printed. These ones are all inkjet printed. There are different printing technologies. I concentrate on inkjet printing at the moment. Screen printing has a much longer history, but there is also a lot of work done to reduce the resolution. In other words, the smaller features you can print, the better. So there is still work done in screen printing as well. I just haven't done screen printing myself. So the printer that I use is on the right top, that's the printer. So it's probably about the size of this lectern, that high. All right. It's not a standard desktop printer, and it is a little bit more expensive, but once again, that technology is also being developed all the time. You do also get room-sized, scaled-up versions for production. Okay, so this is more for research, which is where I'm active. So the top row, those are electrodes. The middle one has a little drop of water on to show that it's a water quality monitoring. I do quite a bit of work in water quality monitoring. Different materials, left-hand one is silver. The middle one, even though it doesn't look like it, is actually gold, but that's it's due to the way the photograph was taken. And the right-hand one is also printed with gold. We can print with platinum, we can print with graphene, we can print with conductive polymers, which in the end might be more friendly. All right. So the middle one, the middle row are examples of where we've integrated off-the-shelf components onto paper. So there's a big picture, and then there's one that's zoomed in on a component, another one that's zoomed in on a chip, and then the right-hand one is an interesting one. That is a chip that we have designed ourselves, had manufactured overseas, and now we're printing the connections to that chip directly, which means our total devices, our packaged devices, are going to be tiny, very, very small. And it works quite well. I'm chuffed. At the bottom are some examples. The left is a device about that size, and it's used for incubating bacteria. So that's a little incubator that we've made with PDMS as a polymer that's often used in diagnostics. Middle one is a circuit on paper. So that's literally just as it would have been manufactured on a PCB, we just manufactured it on paper. And the right-hand one is just showing that these things are flexible. Okay, and we can print conformally. So if we have devices that have shapes, we can print over the shapes eventually, which is also a huge advantage. Okay, so this is now microelectronics in the mind. So we started off in the memory, and then in the moment, and then looking forward is kind of that's still in my mind. Where am I going with all of this? So in the middle is kind of a device that's made paper, plastic, but some cheap device. Sample is the white circle is where we put the sample. Things happen, magic happens. Integrated on that is a printed battery. Integrated on that is a display. Integrated on that, that's at the bottom, around the edge of the bottom paper, is the antenna that's required for communication. Integrated on that are active devices to do the processing that is required. So the idea is that the whole electronic system eventually be integrated on a single device like this. All the technology doesn't exist yet. Much of it is still in research, but as you can see, it's very busy, and I could have made it much, much busier because we do a lot of interesting things. But we're busy with little bits and pieces that would, in the end, all feed into this vision of where we're going with this. And these things are on micron scale. So this is the new microelectronics, as far as I am concerned. The standard electronics has gone, integrated circuit electronics is nanoelectronics. It's 5 nanometers, it's small. It's no longer microelectronics. Okay. Just a little bit bigger than CFM. It's a national program. They're now DSI. I'm still used to calling them DST, so if I slip up, I apologize. So the Department of Science and Innovation, they have a program that's called SARIR, so it's the South African Research Infrastructure Roadmap. And in that roadmap is included a nano and micro manufacturing facility. And we are busy setting that thing up at the moment. The plan is to make it a hub and spoke. At this point in time, the CSIR would be the hub. CFM, for instance, would be one of the nodes on the ends of one of the spokes. And this is an example of how we plan to have devices on all technology readiness levels. So things that are still really, really in basic research, through applied research, directed research, through proof of concept, through prototypes, through all the way to a product that's already coming out of fashion. All of it. And how we're going to, or how we plan to handle it in this facility on different levels. I'm not going to say more about it now. I have a feeling the next speaker, as far as I know, is kind of talking about this whole, there's an association where we're trying to get all the role players involved. I'm from the research side in academia. We have some people from industry. We need more people from industry. There are some people involved from government. We would absolutely love more buy-in. So if you buy my vision and you would like to be part of this, please speak to me. All right, so there's my concluding slide, including the recommendations. So what we do is more than more rather than more of more. We just use the of to do the than. Important there is design solutions. We can design, South Africa can design solutions to local problems, but those solutions are globally relevant. Other people can use what we do. It's good technology, it's good designs. Manufacture in a decreasing number of global fabs. So the normal, and I call that nanoelectronics now, is global. We're not going to manufacture that. But we still have to invest. Research, development, we need the skilled workforce. The two names, additive, well, it was actually advanced manufacturing. I'm changing it to additive manufacturing here, which includes the printed electronics and packaging as part of that. And that is that is the new microelectronics. And then getting to small scale but low cost, and then automated fabrication facilities. The whole 4IR thing, the whole spiel about digitization, this is where it comes in. If we build this with rigorous models for the design and for the fabrication processes, we can have these facilities fairly standalone, and we can go put them where they are needed. And hopefully the communities, those grassroots communities, can then gain economically in the end, quality of life in the end from these facilities. Thank you.